So good evening students. Today we are going to study electrodynamics. So before learning electrodynamics, before learning electrodynamics, we have to know some mathematical preliminaries. The first one we have to know is gradient. The second one we have to know is curl. The third one we have to know is divergence. And the fourth one we have to know is Dirac delta function. So let us see one example. So gradient is a mathematical operation which converts a scalar function to a vector function. So for example, if I write gradient of a scalar, it will convert into a vector. So for example, gradient of x square y z is, first step what you have to do is differentiate this expression with respect to x. So differentiation with respect to x, keeping yz constant. So yz into 2x I cap plus, keep y constant, take y as your variable, x square and z as a constant. So it will be x square z j cap, then take z as a variable, x square and y are constant. So it is x square y k cap. So in this way you can convert a scalar function into a vector function. Next, second term is curl. So the curl is a, before going to curl, let's study about the divergence. So a divergence is a mathematical function which converts a vector into a scalar function. So I just take a example, divergence of f, and let my f vector be x square I cap plus y square j cap plus z square k cap. So when I apply divergence to it, so you have to differentiate this term with respect to x, that will be 2x, plus then this term with respect to y, it will be 2y, plus this term with respect to z, that will be 2z. So here you can see, initially it was a vector, now it is in form of the scalar. There is no I cap, j cap and k cap. So this is about divergence. So curl, the next quantity is curl. So the curl doesn't convert one vector to another vector. So it is a representation, like it will give a orthogonality of the vector. It gives a vector which is perpendicular to the both of the vector. So I will take the same example, curl of f. So when you write curl of f, you have to use determinant, I cap, j cap and k cap. Then dou by dou x, dou by dou y, dou by dou z. Then your first term x square, y square and z square. Okay. So now just take the determinant. So first term, here differentiation of z square with respect to y, it is 0. Differentiation of y square with respect to z is 0. Then j cap. So here also you will get 0. Differentiation of z square with respect to x is 0. X square with respect to z is also 0. Or similarly for k cap also, you can verify it. Differentiation of x square with respect to y 0. So this is a null vector. So there is no vector perpendicular to both this f vector. Okay, so curl 0. So what does it mean? So it means that this kind of vector, this particular kind of vector, what I consider, it is irrotational. It does not rotate. And if you get divergence equal to 0, so in case if you get divergence equal to 0, then the field whatever you have considered vector, it is known as solenoidal. If you get curl as equal to 0, then it is known as irrotational. It means that vector does not rotate. And if you get solenoidal field, it means the vector does not spread. There is no source, or it does not spreading. It is in one way or it is rotating. So it can take any way. Yeah. So we'll go to the next one. It is known as Dirac delta function. Okay. The next important tool in electrodynamics is Dirac delta function. So why Dirac delta function? So what happened is, there is a particular vector function r cap by r square. So what scientists observed was, when you take divergence of these functions and when you take curl of this function, it behaves differently. It behaves differently, weirdly. Okay, so when you take the divergence, you get 0, and when you take curl, you get some non-existing value. So there was some kind of property, such kind of property. So this was the origin for Dirac delta function. So one of the Dirac delta function's important property is, so if I have a function like this, f of r, so whatever I am considering is 3-dimensional, d tau is equal to f of a. So here, whenever you are using Dirac delta function, what happens is, wherever you have delta value, you have to look at this, what are the variables, and you have to select the value of the variable r such that this delta term becomes 0 inside. So inside the delta function, it should become 0. You have to choose such a value. So in this case, r is equal to a. So what happens? The whole integral, the answer will reduce to f of a. Okay, so let us take one example. So one of the example is 2 to 6, 3x square, 2x minus 1, delta x minus 3 dx. Okay, so now how to solve this integral? So what you have to do is, look at this function. Now you have to choose the x value such that the inside term becomes 0. So here suitable substitution is x equal to 3. Correct. After that, what you have to do? Wherever you have x, substitute x. So 3 square minus 2 into 3 minus 1. Here what happens is, this term, whatever here it is, it reduces to 1. Okay, so now what is the answer? This is 27 minus 6 minus 1, 27, this minus 7, so you will get 20 as your answer. So this is your answer. So whatever complicated integral, it reduced to a simple problem. So you can solve this integral by just substituting some values. Okay, to simplify in electrodynamics, to simplify some vector function, we use Dirac delta function. So there are some important identities which you should know. First one is divergence of r cap by r square. Okay, so this is, note that this is not one-dimensional Dirac delta function. This is applicable for 3-dimensional Dirac delta function. So whenever you have like this in 3-dimensional vector function, so you can write as 4 pi delta q r. This is your first important formula, and this is very useful in your upcoming derivations. And the second important formula is this is called Laplacian. So Laplacian of 1 by r is equal to minus 4 pi delta cube of r. So this is the same Dirac delta function itself. You have to choose r value such that it becomes 0 and solve the integral. That's the whole point.